Okay, ladies and gentlemen, good afternoon. I am very happy to welcome you all to our Friday meeting as a part of the webinar series on linear differential problems. Today, I am proud to introduce the distinguished lecture delivered by Professor Vicentiu Radulescu from the University of Craiova and the Institute of Mathematics of the Romanian Academy in Bucharest. The scientific production of
good, like this, on the screen,
devoted to partial differential equations, variational methods, qualitative analysis, equilibrium problems, and applications. He published many articles and books on these important topics. Moreover, he holds the editorial position in several journals of high repute. Professor Radulescu was a highly cited researcher in 2019 by Clarivate Analytics and visited many prestigious international institutes as a visiting professor. He was awarded various prizes. Among them we recall the Simeon Stoilov Prize of the Romanian Academy in 1999, the Prize for Excellence in Research of the Romanian Research Council in 2007. He is a Best Associate Editor of the Journal of Mathematical Analysis and Application in 2009. Today, Professor Radulescu will speak about anisotropic problems with multiphase and mixed regime. Please, Professor.
Professor Radulescu, you have to unmute your audio, please.
Yes. Now it is good?
Yes.
Thank you. Thank you. Please allow me to start by expressing my warmest thanks to Professor Marano for his very kind words about me. Also, I would like to thank all the organizers, because I know that there are several organizers for this wonderful meeting. In fact, I have chosen a talk very related with the contributions of the Italian school, and you will understand immediately why. In fact, I will talk about problems anisotropic, namely with variable exponent, with multiphase and mixed regime, and I will explain immediately why. Good. Anyway, the content of my talk is more or less included in this paper with Alves, published in the Proceedings of the American Mathematical Society. Several related papers about double phase problems are mentioned here, published in the last few years, and I conclude, you see, with the paper which will be published soon again by the Proceedings of the American Mathematical Society, this time about the Shocard problem. So these are my papers, and now just a very few related references, mainly you see by the Italian school, the pioneers of the field, Professor Marcellini, Professor Mingione, Professor Pucci, to mention only a few of them, because the Italian school is very, very strong, not only in double phase problems, but also in analysis. A lot of huge contributions in analysis. Due to the fact that I will speak about problems with variable growth, I start by saying that, to the best of my knowledge, problems of this type were were introduced for the first time by John Ball in relationship with the problems arising in nonlinear elasticity, in composite materials. In fact, John Ball studied integrals of this type where f is a sum of functions with different contributions. For instance, j is like c to the power p, while h doesn't have a precise growth. Namely, we say only that h goes to plus infinity here. So problems of this type were introduced by John Ball in strong relationship with the concrete applications. And a little bit later, Zhikov, in the context of homogenization, studied strongly anisotropic materials. In fact, he introduced 3 types of energy functionals. You see, the first one is very related to the Laplace operator, the second one to the px Laplace operator, which is a non-obvious generalization of the p Laplace operator, while the last one is really a double phase problem. You see, there are 2 terms. The first one is associated to p Laplace operator, and the second one to the q Laplace operator. And the problems of this type were studied by Zhikov and by several mathematicians in relationship with the Lavrentiev phenomenon. Here there are some details. This terminology, PQ type problems, appears for the first time in the papers of Paolo Marcellini, where the integrand is controlled by C to P and by C to Q, where P is less than Q. In fact, what is the basic idea? The last functional introduced by Zhikov is a double phase energy. And in a conference, but this is the so-called isotropic. Isotropic in the sense that P and Q are constant. In a conference organized in Perugia in September 2016, Rosario Mingione proposed me to study related problems, but by replacing P by P of x and Q by Q of x by variable exponents, and you will see immediately that really new phenomena appear in this situation. Something about spaces, function spaces with variable exponent. In fact, the regularity of the potential P is very important in problems of this type. In my talk, I will assume that P is very smooth. We don't have problems of this type. In fact, Zhikov observed that an realistic regularity assumption is to assume that P is logarithmic Hölder continuous, as it is defined here. So Px minus Py is controlled by a constant over the logarithm of the distance between x and y. In this situation, we don't have any problems. Otherwise, there is the so-called Lavrentiev phenomenon, in the sense that we don't have the density of smooth functions in the corresponding Sobolev space. But if we have a regularity assumption of this type, we don't have any problems. Also, if P is logarithmic Hölder continuous, we have the Poincaré inequality, and so on, a lot of results, classical results. In the case where the domain omega is bounded, there is a strong relationship between these 3 spaces, namely the space of Lipschitz functions, the Sobolev space with high exponent, Q bigger than the dimension of the space, and the space of logarithmic continuous functions. In the case where omega is not bounded, the definition of logarithmic Hölder continuous functions should take into account the behavior at infinity. And this is described here. So the distance between Px and Py at infinity is controlled by a constant over the logarithm of 1 plus a modulus of x or something like this. However, in this situation, where omega is not bounded, we cannot have a relationship between the spaces of this type, because, for instance, P, we cannot require that P is in W1Q due to the fact that this integral equals to plus infinity. That is why for spaces of this type, in this situation where omega is not bounded, we introduce usually another space, which is defined here, a Sobolev type space, and the conclusion is that these three hypotheses are completely independent in the case of unbounded domains. But it is not the purpose of my talk to give details in this direction. In fact, I shall start with a very simple problem, a very classical problem, just to give an idea about my talk. So I shall start by this problem, minus P Laplace of U equals a power type nonlinearity, modulus of U to the power Q minus 2 multiplied by U in omega. We assume that P and Q are bigger than 1. We assume Dirichlet boundary condition, and of course we are looking for non-trivial solutions. This problem, very classical, the solution strongly depends on the relationship between Q and the critical exponent, Sobolev exponent associated to P. So P star, which is NP over the dimension of the space minus P, assuming that P is less than 1. Why? Because we can distinguish exactly one of the following three cases. The first one, the subcritical case corresponding to Q less than the critical Sobolev exponent of P. In this situation, we can obtain an energy which is coercive, namely if Q is less than P. In this situation, we have a solution by the direct method of the calculus of variations, or we can have a mountain path geometry if Q is bigger than P. So the problem has again one solution, also due to the compactness. And the case P equals Q corresponds to an eigenvalue problem. So here we can have or not solutions of the problem. So this is a subcritical situation. The critical situation corresponding to Q equals P star. In this situation, all depends on the topology of the domain omega. This plays a crucial role. For instance, in the linear case, semilinear case, P equals 2, N equals 3, and Q equals 6. And if omega is not contractible, then our problem has at least one positive solution. Here, we can cite the pioneering papers by Rezis, Nirenberg, and so on. The supercritical case corresponds to Q bigger than P star. This situation is delicate, is difficult, and the key role is played by the geometry of omega. For instance, if omega is star-shaped, then by Pohozaev, we don't have any solution. However, if omega is an annulus, for instance, our problem has at least one solution. So we can distinguish in this isotropic case exactly one of these three situations. So we have this diagram. The blue color corresponds to the subcritical case, the red color to the critical case, and the green one to the supercritical case. So this is valid for P and Q constant, real numbers. What happens now if we replace P by a function which is not constant, depending on X, and Q again by a function depending on X? In this situation, the P Laplace operator is replaced by the Px Laplace operator, which appears here, which is defined here. And the corresponding critical exponent depends also on the point. So n P of x over n minus P of x. if P of X is less than N. What happens in this situation? I shall start by a very simple example. Consider the Lane-Emden problem with a parameter lambda, which is here, minus px Laplace of u equals to lambda modulus of u to qx minus 2u in omega with Dirichlet boundary condition, and we are looking for non-trivial solutions. Let us assume that we are in the subcritical case everywhere for all points in omega up to the boundary, and let us assume that the minimum of P, which appears here, is between the minimum of Q and the maximum of Q. A situation of this type cannot appear in the case of constant exponents because Q is constant, so we cannot have an hypothesis of this type. In this situation, the problem is subcritical in every point. We can prove the existence of solutions in the case of low perturbations of the right-hand side of the reaction. Namely, there is some lambda star positive such that we are sure that our problem has a solution for any lambda positive but less than lambda star. And all depends here also on the domain, on the variable exponents px and qx and so on. So we cannot say normally what happens for any lambda here because of the fact that since P and Q are not constant, the associated energy is not coercive. Maybe it is coercive in some points. It doesn't have the mountain pass geometry, so it is possible to prove the existence of solutions only for small perturbations. So let us keep in mind this problem, this standard problem. But you see that assumption H2 says that our problem is subcritical in every point. However, due to the fact that P and Q are not constant, it is possible that our problem, in fact, this one, if you want, problem 3 is without lambda. It is possible to have a mixed regime in the sense that a problem of this type with variable exponents becomes subcritical in some subdomain of omega. It is critical in another subdomain of omega and supercritical in another subdomain. So the same problem can be at the same time subcritical, critical, and supercritical. And just to give you an idea, this diagram, you see, this diagram shows that the problem is subcritical in the blue region. It is critical in these points, in several points, even in some regions eventually, and it is supercritical in the red region. So this is a problem with mixed regime. And this is possible to have something like this because we are in the anisotropic case, namely P and Q are not constant, are variable functions. In this situation, you see P and Q depend only on the point, but it is possible to consider anisotropic case depending on the directions and so on. The situation is very, very complex here, so we can cover a lot of cases. So I was interested to start a study of problems of this type and to try to understand better, to find sufficient conditions for the existence of solutions. And I shall give you 3 examples here. For the same problem, the radial case, the non-radial case, and the singular case. And I shall explain immediately why. I shall start with the radial case corresponding to the ball. Here we define several exponents. You see P is non-constant, M is also a variable exponent, A, another potential, is between 0 and L. We assume that P, A, and Q are radial functions, as defined here in hypothesis H3. And we also assume something very interesting, which will show, in fact, the nature of our problem. We assume that the new exponent, variable exponent q, is non-negative as it is stated here, but we assume a local hypothesis in the sense that there is some small r less than the radius of the ball, such that on this small ball, the minimum of q, denoted by qr minus, is strictly bigger than the global maximum of p, so p plus, this is the global maximum of p, which is defined here, the maximum with respect to the initial ball. And also we assume that the maximum, the local maximum of q on the, with respect to the small ball, denoted by qr plus, is strictly less than the global minimum of the critical exponent of p with respect to the whole domain. Omega is, in this case, of course, the ball. So these are the assumptions. We are in the radial case. What we observe that due to these assumptions, q is subcritical in the small ball, but there is no hypothesis with respect to q outside the small ball, namely in the annulus, defined by the big ball, initial ball, and the small ball. So here, q can have any behavior, even a supercritical behavior close to the boundary, because we are more or less close to the boundary. Anyway, what we can point out, so our problem, I shall give you immediately the details. We have a continuous embedding. We also have a compact embedding due to the fact that we are working with radial functions. And we have embeddings of this type. This is more or less standard. This is not a problem. What it is important is that we have a compact embedding of the Sobolev space of radial functions W1px is compactly embedded into LQX with respect to the ball. Now we define the operator. We have, in fact, an operator with two variable potentials, m of x and a of x, which appears here. And the space where we are looking for is a space W1px0, intersection W1mx with respect to the new potential a of x. Here we introduce the norm, which is a Luxembourg norm, and in fact we consider the norm on our space E, the contribution with respect to the first space, and with respect to the second space, the norm is defined here, so we take into account both contributions, and this is natural. We point out that if A equals to 0, then our space is W1px0. Very good. So we have again some contributions of this type. We are looking for the following problem, which is a slight extension of the lane Emden problem. So without the second differential operator, we have exactly the lane Emden problem with variable exponents, px and qx. But if we add this new operator, we shall obtain a double phase problem with variable exponents. So a double phase problem with variable exponents associated to the standard lane Emden equation with variable exponents. We are on the ball, and again we assume the same boundary condition, u equals to 0 on the boundary. So the result in this situation is the following. Under the previous hypothesis, our problem has at least one non-trivial solution. What is the basic idea? The basic idea is to apply the Palais principle of symmetric criticality, which says that more or less critical symmetric points are in fact symmetric critical points. In a rigorous statement, this principle says that if we are, in the case of Banach spaces, having a symmetry group G, and if J is a G invariant functional defined on the Banach space X, then the conclusion is that every critical point of the functional restricted to the subspace of symmetric points becomes, in fact, a critical point of the functional with respect to the whole space. So this is our first main result. This is a statement of Palais' principle of symmetric criticality, but is a basic idea. In a natural way, the energy function associated with our problem is defined here. This is standard. What about the properties of this one? The main difficulty is that this function is not well defined, because we have seen that in the annulus, we don't have any growth assumption about Q, so we cannot say that this integral is well defined. That is why, at the beginning, we shall restrict the energy function with respect to the space of radial functions. And in this situation, the function is well defined and the derivative is given here. So, in this situation, our energy function satisfies a mountain pass theorem and also the Palais-Made condition because of the fact, as I said to you at the beginning, we have a compact embedding. So we can establish the existence of a non-trivial critical point with respect to the space of radial functions. Our idea is to prove that, in fact, this critical point is a critical point of the energy with respect to the whole space. The difficulty here is that we cannot apply directly the Palais principle of symmetric criticality because our energy is not well defined in the whole space E. That is why we shall use a truncation of the nonlinear term. Namely, we consider the function G depending on X and T, which is defined here. We take the function xi of X, which is defined here, namely xi of X equals to 1 in the ball of radius r over 2 in a very small ball around the origin, and the 0 outside the ball of radius 3r over 5. And we take this truncation, and corresponding to this truncation, we associate what it is important is the fact that the behavior of G defined here is described by this inequality. This means, in fact, that G has a subcritical growth. So in this case, we define a new Dirichlet problem corresponding with this truncation. So we keep the left-hand side, but we modify only the reaction, the right-hand side. Here, the energy is defined in this way. And due to the fact that G is subcritical, as we have seen, our new energy is well defined with respect to the initial space, E. J is of class C1 with respect to this space. Standard straightforward computation shows that the derivative of J is defined in this way. And now we use the fact that J of X and Ux is defined in this way for X in BR. So in fact, U is a critical point of J restricted to the space of radial functions. And only at this moment we apply the Palais principle of symmetric criticality to show, in fact, that U is a non-trivial critical point of J in the whole space. So this is our first example of the case of balls, the radial case. Now we keep the same problem and we replace the ball with the general domain, absolutely the same. More or less, we have some similar hypotheses. I shall recall some of them. Here, it is much more difficult. There are more difficult technical details, but I should give just general ideas. We assume that there is a number r and a number capital R such that the ball of radius capital R is included in omega, and we assume that the potential A, which appears in the expression of the second differential operator, is constant with respect to the annulus, which is defined here. Again, we assume that P and M are variable exponents, and A is another potential, which appears here with this hypothesis between 0 and L. And again, we assume that P and Q are radial, have radial symmetry, but only locally with respect to the annulus, which is defined here. So we have local symmetry hypothesis with respect to the variable exponents. Okay, very good. As until now, more or less, we have an hypothesis, a local hypothesis about the variable exponent Q, which is a little bit different, has some similarities with the previous assumption. You see here we are looking for the minimum of the variable exponent Q with respect to the exterior of the annulus, and we assume that this one is bigger than P plus, and the maximum of Q with respect to this set is less than the minimum of the variable of the critical exponent of P. So we point out the fact that we do not assume any growth assumption on Q in the annulus. So this means that Q can have a supercritical growth in this region. Under this hypothesis, the theorem shows that with respect to these assumptions, our problem has a non-trivial solution with respect to the space E. Some details, just a few details about the proof. The energy functional, again, the problem has a variational structure. We associate to the problem this energy, which is defined here. Again, we cannot say that the energy is well defined due to the problems created by Q. That is why we shall restrict this time the energy to the closed space, subspace X of E, consisting in functions which are radial with respect to the annulus. Now, applying the mountain pass theorem of Ambrosetti and Rabinowitz, we obtain a non-trivial critical point denoted by U0 in X with respect to this closed subspace of our energy function. Next, we show, in fact, that this critical point is a critical point of our energy, so a solution of our problem. Again, we cannot use a Palais principle of symmetric criticality because omega is not a ball, but however, the idea is the following. We consider this new space consisting of the functions on in X such that U equals to 0 on the boundary of the annulus. So by multiplication with the test functions of this type, we obtain something like this, a relation, variational identity of this type. And then by using cutoff functions and density arguments, we conclude that U0 is a non-trivial solution. So anyway, the proof is longer, but these are the key points of the proof in order to avoid the fact that the domain this time doesn't have any symmetry hypothesis. And I shall conclude with a completely different situation. In fact, we keep the problem. We keep the problem. We have here a parameter. There is a same double phase problem with several variable exponents. And this is more or less a bifurcation problem or something like this, even if we shall obtain only a partial result in this direction. So we are interested only in proving sufficient conditions for the existence of solutions. In this situation, we assume that again there are two numbers r and capital R, such that the ball of radius capital R is included in omega, and the annulus is included in omega delta, where omega delta is a subset of omega such that the distance of the points x to the boundary of omega is strictly bigger than delta. So we are far away from the boundary of omega, and we assume, as in the previous case, that A is a constant function, but only with respect to the annulus. What happens here? This is the same assumption, assumption H9. Assumption H10 is more or less until now. But here you see that we compare with the QA minus, the minimum of Q with respect to the exterior of the annulus, and also with respect to omega delta, so we are a little bit far away. This one is strictly bigger than the maximum between the maximum of P and the maximum of M. And again, the maximum of Q with respect to the same domain is strictly less than the minimum of the Sobolev critical exponent with respect to P. Very good. Now, what happens about Q? What happens about Q? We assume that Q is again greater or equal to 0, but the novelty is the fact that we assume that the limit of Q as a distance from x to the boundary of omega goes to 0 equals to 0. So in fact, Q vanishes on the boundary of omega. But what happens if Q vanishes on the boundary of omega? If we are looking here in the reaction, we see that in this situation, our problem is singular. The nonlinearity that appears here becomes a singular nonlinearity, like U to a negative power. So this time, we have a double phase problem with variable exponents, anisotropic, and with the singular nonlinearity on the boundary. Again, with mixed regime, and we shall see. So, the hypothesis, the main result is the following one. In this situation, we can say only the fact that for small perturbations of the right-hand side of the reaction, we are sure that we can obtain a solution. Namely, for any lambda small enough, our problem has a solution. But even more, we can say that if lambda is small enough, our problem has not only one solution, but at least two non-trivial solutions. And we shall be able to prove that there are at least two non-trivial solutions by using variational arguments and by obtaining different levels of energy. So, the proof is the following. We associate again this energy functional, which is defined here. We repeat more or less the fact that this one is not well defined due to the problems created by Q. We restrict this energy to the same subspace of functions with radial symmetry with respect to the annulus. So I is of class C1 and satisfies the Palles-Mail condition. And there are some preliminary results which are very interesting. The first one, you see, the first one says that, in fact, our energy functional satisfies one of the geometric assumptions of the mountain pass theorem. In fact, this shows the existence of a mountain. The level of the energy is at least rho on the sphere of radius tau, uniformly with respect to lambda small enough. So this means the existence of a mountain near the origin, and what it is important, uniformly with respect to lambda. The second preliminary result says the following. If we denote by A lambda the infimum of the energy with respect to the closed ball of radius tau, which appears here, then A lambda is strictly less than 0, again, uniformly with respect to lambda. So this means the existence of a valley, but the problem is the following one. In the statement of the mountain pass theorem, the valley should be on the other side of the mountain. So the mountain should be between the first village, the origin in this case, and the second village, the valley, which appears here. So this is a problem. That is why we don't have, in fact, a mountain pass geometry. We have only one of the geometric assumptions satisfied. But in fact, we can apply in this situation the Eklund variational principle, which will imply the fact, the existence of almost critical points, in fact. And finally, we obtain U lambda, which is a critical point of the energy, and the corresponding energy level is this one, A lambda, defined in the second lemma, and this is negative. So we have a critical point of our energy, of our function for any lambda less than lambda star. Now we continue. Another preliminary result shows that if we fix phi in a good way, in a clever way, namely in C0 infinity omega delta minus the annulus, and if we take the limit of the energy computed at the point t phi, this one goes to minus infinity as t goes to plus infinity. So this means, in fact, that we have a kind of mountain pass geometry in a strict way. This means that for almost every lambda less than lambda star, there is a bounded Pallas-Mail sequence corresponding to the corresponding min-max critical level for the energy. This C lambda is a mountain pass level of the energy. Due to the fact that we have the Pallas-Mail condition, we deduce that for almost every lambda less than lambda star, C lambda is a critical value. So we have something like this. And the corresponding critical level C lambda is strictly positive. So due to the fact that for Eklund we have a negative energy, for mountain pass a positive energy, we conclude, in fact, that we obtain for lambda small enough two different critical points, so the problem has at least two solutions. You see, this is just a result showing what happens in the case where lambda is small. I do not have a complete characterization for any lambda to establish what happens for any lambda. And I shall conclude with some open problems which are very related with the content of my talk. The first one is the following. A very important type of operator is a so-called Bauendi-Grushin operator, which is, you see, in fact, a generalization of the trichomy operator, an elliptic hyperbolic operator. This time is with the variable exponents. You see, the variable exponent here is j, depending on x and y. In fact, we split the space Rn into Rm and Rk. X is in the first space, Rm, the second y is the second space, and we have the divergence with respect to the first variable, x, and here with respect to the second variable. Here we have also a potential which could be degenerate in the sense that x is vanishing. So this is more or less, if you want, a kind of px, qx variable operator with variable exponents. So this is a very non-trivial generalization of the PQ problem for variable exponents. But it is much more than this because the problem has a very complex structure. So I do not have existence results for Bauendi-Grushin operators with variable exponents and with mixed structure, namely subcritical, critical, supercritical problems, as I have mentioned for the case of the px Laplace operator. Also, I don't have any idea about biharmonic operators with mixed regime. So what happens if we replace the problem by a double phase problem, but replacing the Laplace operator with the biharmonic operator? Also, there are just a few contributions about double phase fractional anisotropic Kirchhoff problems, but I don't know what happens if we have problems with mixed regime like this one. Also, Shockhard problems with mixed regime, this is very little known. There are not many results. I don't have something of real interest. And of course, heat equations with mixed regime. I know that Claudiano Alves has some contributions in this direction, but we are very far from a very good understanding of the problems of this type. And I would like to thank you very much for your attention.
Thank you very much to Professor Radulescu for the very nice conference.
Thank you very much.
Are there comments, questions?
There are plenty of open problems. You see, there are plenty of open problems in this direction, and we are very far from a good, complete understanding of the problems of this type. So anisotropic double phase problem can create really new phenomena that cannot appear in the case of constant exponents.
If not, or for the moment not, I have just a curiosity.
Yes.
Vicentiu, is it
Yes.
possible to replace the bounded domain omega with the whole space Rn?
Okay, this is a very good question. And this is in the list, we can include this problem in the list of open problems. So I was interested in taking into account the classical problem. The classical problem is for bounded domains and so on and so on. And just to replace P and Q by P of X and Q of X. If we have only one operator, this is important. If we have only one operator, we don't have problems of this type. So it is crucial to have in the left-hand side two operators with variable exponent. So we obtain these new phenomena due to the fact that we have two operators with variable exponent. In the case of the whole space, for instance, so we don't have a Dirichlet boundary condition, we don't have compactness, so we should be very careful to keeping some compactness. That is why at the beginning I assumed that P and Q are radial functions and so on. So there are plenty of open problems, but I assume that we can try to do something in this direction. So I try to raise these open problems because there are many experts in the field attending this talk, and maybe they will try to see. Anyway, I haven't studied the case of the whole space in this direction, so I don't have any idea in this direction. As far as I know, these are really the first results in this direction. Double phase problems with variable exponent and with mixed regime. It is interesting to study what happens if we consider a mixed regime, because the functional is not well defined and so on and so on. This is a first direction. But anyway, we can consider problem without a variational structure. What happens if we have problems without a variational structure? Here, we have played with the Ekland variational principle with mountain pass, direct method, and so on. Otherwise, I don't know. I don't know. This is really an open problem.
Okay, Thank you.
But I shall try to look in the future, also in this direction.
Are there other comments, questions?
May I ask a question?
Yes.
Professor
Antonio.
Radulescu, good evening.
Yes.
First of all, thanks for the very, very interesting seminar. And I was wondering, in the basic case with only one variable exponent operator and the mixed regime in the Q exponent of the reaction, you want to apply Palais principle, and you have this problem of the functional that is not properly defined on the whole space.
Yes.
And what happens if we, I don't know, give a sort of non-smooth framework like they did in some cases where the functional is only differentiable on some directions? Did you even figure out, or
no, so okay, very good. So the basic idea here is to replace the standard Frechet differentiability by Clark subdifferential generalized gradient and so on.
Like
no, I haven't studied, but for sure. So in this case, we replace, of course, with an inequality problem, because we take the Clark generalized derivative and so on. No, I was not, I haven't studied until now. I was interested only in finding some results, some sufficient conditions showing that we can handle what happens even in the case of supercritical problems. There are only sufficient conditions. They are not, it would be marvelous if we can find necessary and sufficient conditions, of course, but this is very far away. You see, and another problem is the fact that P and Q are assumed to be smooth. We don't have problems with the density of smooth functions into Sobolev spaces. Otherwise, we can obtain completely different problems, another kind of difficulty due to the lack of regularity of the potential. So that is why I said that there are plenty of difficulties of open problems and so on. But also this one with the lack of regularity of the associated energy, this is another problem. And also we can work in this direction, I think.
Thank you.
Thank you.
Well, other comments, questions? If not, we thanks again Professor Radulescu. Thank you very much.
Thank you very much.